Assalamualaikum and a very good day to all students that are taking this course, which is process instrumentation. For today lecture, we are going to go through the previous lecture, which I have postponed it in slide number 22. For today, this is continuity for the first chapter, for part two of this chapter. So today we are going to recap about the previous chapter, about the previous part, which I already give you the lecture regarding this topic. Okay, so as a quick recap, so we will need to we need to know that there is a lot of transducer that in market. So when there is a lot of transducer in the market, so there is a lot of selection of the transducer that you need to consider when selecting the best transducer to be used in the environment that you wanted. Okay, there are a lot of factors that affecting the choice of transducer instrumentation and process control. Okay, such as operating principle, sensitivity, operating range, accuracy, error, transient and frequency response, loading effects, and also physical environment. In the case of operating principle, the transfer are so many times selected on the basis of operating principle used by them. Okay, the operating principle used in the transducer may be sensitive, maybe resistive, inductive, capacitive, optoelectronic, piezoelectric, electric, and so on. In terms of its sensitivity, you need to look into the transducer must able to give you a sufficient output signal per unit of a measured input in order to yield meaningful data. Meaning that you must ensure that the transducer that you select can have a good sensitivity in which it gives you a sufficient output signal so that it can be transferred into a meaningful data in which you can interpret and work on. Okay. Another factor that you to consider when selecting a transducer is the operating range. Okay, the transducer should maintain the range requirement and have a better resolution over its entire range. Okay, in terms of accuracy, high degree of accuracy is necessary for measurement. In the perspective of error, okay, the error inherent in the operation of the transducer itself, but it should maintain the expected input output relationship as described with its transfer function as to avoid error. Okay, in terms of transient, the transducer should meet the desired time domain specification as well as it should ideally have a flat frequency response curve. So this is that you need to look into when you are choosing a transducer in terms of its transient and also the frequency response. In terms of the loading effects, okay, to avoid loading effect, it is necessary that a transducer has a higher input impedance and a low output impedance. So you need to consider this. When choosing a transducer, you must have a transducer that give you minimal or it can avoid the loading effects. Okay. In terms of physical environment, when choosing a transducer, you must select the transistors that are able to work under specific environmental condition and maintain its output-input relationship so that it can give you the meaningful data. So this is the factor that you need to consider when choosing a transducer in the field of process and instrumentation. This is the end of part one, which I already recap about the part one. So and then we proceed with part two. Okay, for part two, okay, for part two, okay, we will be looking into the scope of type of sensor. Okay, there are a lot of sensors are available. So, however, it is being classes into different classes. Okay, so the first one is temperature and heat type of sensor. Okay, temperature is a measure of the thermal energy in a body, which is relative hotness or coldness of the medium, and is normally measured in degree using one of the following scale. So you can use this following scale to measure the temperature, which is Fahrenheit, Celsius or centigrade, Fahrenheit, and also Kelvin. Okay, absolute zero is the temperature at which all the molecular motion ceases or the energy of the molecule is zero. So it's known as absolute zero. Okay. The need to convert from one temperature scale to another is a very common in everyday occurrence. Okay, the conversion factor are as follow as shown in the below. Okay, how to convert Fahrenheit to Celsius, how to convert Celsius to Fahrenheit, how to convert the Fahrenheit to Rankine, how to convert Celsius to Kelvin, and so on. Okay. Heat transfer is the amount of heat needed to raise or lower the temperature of a given weight of a body can be calculated from the following equation. So this equation exhibit on how you can calculate the amount of heat needed to raise or lower the temperature, okay, of a given specific weight of body. Okay, where W represent weight of the material, C represent the specific heat of the material, T2 represent the final temperature of the material, whereas T1 represent the initial temperature of the material. As always, care must be taken into selecting the correct units. Okay, negative answers indicate extraction or heat loss. So you get negative answer in your calculation. So meaning that there is a heat loss from the materials. Okay, heat conduction through a material is derived from the following relationship, whereas Q is equal to rate of heat transfer, K equal to thermal conductivity of the material itself. Okay, A is the cross-sectional area of the heat flow. T2 is the temperature of the material distant from the heat source, whereas the T1 is the temperature of the material adjacent to the heat source, whereas L is length of the path through the material. Okay, so the note here is given if the negative sign in the negative sign in the equation represent that there is a positive heat flow in the material itself. Okay. Heat convection calculation in practice are not as straightforward as a non-conduction. Okay. However, convection is given by the below equation, whereas Q equal to convection of heat transfer rate, H equal to coefficient of heat transfer, whereas A is the heat transfer area, TO2 minus T1 is the temperature differences between the source and the final temperature of the flowing medium. Heat radiation depends on the surface color, texture, shape involved, and the light. Okay. Hence, more information that the basis relationship for the transfer of radiant heat energy given below should be factored in. Okay. So the radiant heat transfer is given by the below equation. So you can use this equation to calculate the radiant heat transfer. Okay. Okay, this slide show you the example how you yeah, show you the example of a scenario in which a furnace wall with 20 feet in area and 6 inches in thickness has a thermal conductivity of 0.14. Okay, what is the heat loss if the furnace temperature is 1100 degree Fahrenheit and the outside of the wall is 102 degree Fahrenheit? So this calculation, this example is also being accompanied by how you going to calculate, okay, the scenario. So is I'll give you a lot of example together with the solution to give you better understanding what is the what how to calculate and how to solve the specific problem in normally encounter in normal life. Okay. Okay. Temperature measuring device. Okay, there are several methods of measuring temperature that can be categorized as follow. Okay, expansion of material to give a visual indication, pressure or the dimensional change, and then electrical resistance change, semiconductor characteristic change, voltage generated by similar method, and also radiated energy. So there is a lot of temperature measuring devices. So it can be categorized into 5 categories depending on their fundamental or how they works. Okay. Okay. For thermometer, okay, thermometer is a temperature measuring device. Okay, thermometer is basically have a mercury in it. So mercury in the glass was by far the most common direct visual reading thermometer, if not the only one lah. However, the device consists of a small bore radiated glass tube with a small bulb containing a reservoir of mercury. Okay, the coefficient of expansion of mercury is several times greater than the coefficient of the expansion of glass. So that as the temperature increases, okay, the mercury also rises up and the temperature can be giving a relatively low temperature and accurate method of measuring temperature. So this is the fundamental how the thermometer work in measuring temperature. Okay. Okay, these thermometers are used where remote indication is required, as opposed to glass and bimetallic devices which give reading at the point of detection. Okay, the pressure spring device has a metal bulb. Okay, metal bulb made with a low coefficient expansion material with a long metal tube. Both contain material with a high coefficient of expansion. Okay, the bulb is at the monitoring point. Okay, the metal tube is terminated with a spiral bourbon tube pressure gauge scale in degree as shown in figure 8.4. So that you can see here how the bourbon tube pressure gauge is it terminate the metal bulb with a spiral bourbon tube that work as a pressure gauge. Okay, the pressure system can be used to drive a chart recorder, actuator, or a potentiometer wiper to obtain an electrical signal. Okay, so as the temperature in the bulb increases, the temperature in the system rises. The pressure rise being proportional to the temperature change. Okay, the scale is pressure. The change in pressure is sensed by the bourbon tube which is in the form of spiral, and converted to a temperature scale. Okay, this device can be accurate to 0.5% and can be used for remote indication up to 100 meter, but must be calibrated as the steam and the bourbon type are temperature sensitive because they are both sensitive. So you need to calibrate it at first before it can be used. Okay. So there is another type of temperature detector which is known as resistant temperature detector or RTD. RTD is a temperature sensor that is based on the principle discussed in the preceding section. That is metal resistant increasing with temperature. So when the temperature increase, the metal resistance also increase proportional to the temperature. Okay. So the metal used in this type of device vary from platinum, which is very repeatable, quite expensive and very expensive compared to nickel. Which is nickel have a good characteristic, which is although it's not quite as repeatable as platinum. However, it is more sensitive and also it's also less expensive compared to platinum. So this diagram show you this example of resistant temperature detector. Another type of temperature detector is the signal conditioning. Okay, in a view of a very small fractional change of resistance with temperature, the RTD resistant temperature detector is generally used in a bridge circuit. So this is the bridge circuit. Figure illustrates as the essential feature of a such system. Okay, the compensation line in the leg of the bridge is required. So this is the compensation line. When the lead length are too long, that the thermal gradient along the RTD leg may cause the change in the line resistance. Okay, these changes show up as a false information, suggesting change in the RTD resistance. So by using the compensation line here, the same resistance change also appear in RT here, side of the bridge, cause no net shift in the bridge null. Okay. So dissipation constant. Okay, because RTD is a resistant, there is I squared I to the power of 2 multiplied by R. Power dissipated by the device itself that cause a slight heating effects, which is known as a self-heating phenomena. Okay, this may also cause a erroneous reading or even upset the environment in a delicate measurement condition. Okay, so it might give you error reading. Thus, the current through the RTD must be kept sufficiently low and constant to avoid self-heating. Okay. Typically, a dissipation constant is provided in a RTD specification. So, in order to avoid self-heating, the RTD devices are normally being equipped with dissipation constant. Okay. This number related the power required to raise the RTD temperature by 1 degree of temperature. Okay. Thus, a 25 milliwatt dissipation constant show that if I squared I to the power of 2 multiplied by R, power losses in the RTD equal to 25 milliwatt, the RTD will be heated by 1 degree Celsius. Okay, so the dissipation constant is usually specified under two conditions: free air and well-stirred oil bath. Okay, this is because of the difference in the capacity of the medium to carry heat away from the device. The self-heating temperature rise can be found from the power dissipated by the RTD itself, and the dissipation constant form can be represented by the below equation, whereas uh, delta T is representing the temperature rise because of the self-heating in degrees Celsius unit. Okay, P is the power dissipated in the RTD from the circuit in watt. Okay, whereas PD dissipation constant of the RTD in watt over degrees Celsius. Okay, so this slide show you an example how to calculate the RTD. Okay, so it also the slide is also being accompanied with a solution to show you step by step how to calculate the above problem. Okay. Another type of temperature measuring device is a thermocouple. Okay, thermocouple are formed when two similar metals are joined together to form a junction. Okay, and a electrical circuit is completed by joining the other end of the similar metal together to form a second junction. Okay, the current will flow in the circuit if the two junctions are at different temperature as shown in figure below. Okay, we have figure side. Okay, you can see here when the two junctions are joined and there are differences temperature between the two junctions, the current will flow. Okay, the current flowing is the result of difference in the electromotive force developed at the two junctions due to their temperature differences. Okay, in practice, the voltage difference between the two junctions is measured. The difference in the voltage is proportional to the temperature difference between the two junctions itself. Okay. Note that the thermocouple can only be used to measure temperature differences. Okay. However, if one junction is held at a reference temperature, the voltage between the thermocouple give a measurement of the temperature of the second junction. Okay. Three effects are associated with thermocouple. They are as follow. The first one is the seatback effect. Okay. It states that the voltage produced in thermocouple is proportional to the temperature between the two junctions. Another type of effect that associated with thermocouple are Peltier effect. It states that if a current flow to a thermocouple, one junction is heated and put out of energy, and the other junction is cool. So one junction is heated, another junction is cool. Okay, so this is known as Peltier effect. Another effect is known as Thomson effect. Okay, it states that when a current flow through a conductor along which there is a temperature differences, heat can be produced or it can be absorbed depending upon the direction of the current and the variation of the temperature. So according to Thomson effect, when current flow through, the heat can be produced, it can be absorbed. However, it must depend on the direction of the current and the variation of the temperature. Okay. Another type of temperature sensor is the thermistor. Okay, the thermistor represents another class of temperature sensor that measure temperature to change of material resistance. Okay, the characteristics of this device are very different from those of RTD and depend on the peculiar behavior of the semiconductor resistance versus temperature. So this is another example of thermistor. So the word thermistor is a combination between thermal and also temperature between the thermal and also conductors known as the combination is known as thermistor. Okay. Because a thermistor exhibits such a large change in resistance with temperature, there are many possible circuit applications. So for thermistor, you can apply a lot of circuit application because the large change in resistance of temperature. Okay. In many cases, however, a bridge circuit is used because the non-linear feature of the thermistor make its use difficult as an actual measurement device. Okay. Because these devices are resistant, care must be taken to ensure that the power dissipation in the thermistor does not exceed the limit specified or even interfere with the environment for which the temperature is being measured. Dissipation constant are quoted for thermistor as the power in milliwatt required to raise a thermistor temperature above its environment. Okay, typical value varies from free air to 10 milliwatt or more in an oil bath. Okay, so depending on the value, they are typical the value ranging depending on whether in the environment, whether it's in the free air or it can be in an oil bath. So this slide show you an example of problem solving. Okay, it being accompanied together with solution in which you can go through how to solve the problem. Is step by step solution. So to give you clear understanding how the thermistor works and how the thermistor is being used to calculate the temperature. Okay. Another type of temperature sensor is the semiconductor. Okay, semiconductor have a number of parameters that vary linearly with temperature. Okay, normally the different voltage of a Zener diode or junction voltage variation are used for the temperature sensing. Okay, semiconductor temperature sensor have a limited operating range from -50 to 150 degrees Celsius, but are very linear with accuracy plus minus 1 degree Celsius or better. Okay. Other advantage are the electronic can be integrated onto the same die as the sensor giving output giving high sensitivity. Okay. Easy interfacing to control system and making different digital output configurable possible. Okay. The thermal time constant varies from 1 to 5 seconds. Internal dissipation can also cause up to 0.5 degrees Celsius offset. Okay. So thermal devices are also rugged, okay, with longer activity and are very expensive. So meaning that this type of temperature sensor is very capable and very durable. Okay. For the above reason, the semiconductor sensor is used extensively in many applications, including the replacement of mercury in a glass thermometer. So due to its durability, sensitivity, and also its accuracy, efficiency, semiconductor is now replacing a lot of temperature sensor because it's more preferable by the market due to its durability, high sensitivity, and etc. Okay. So for the selection, okay, in process control, there is lot of wide range of temperature sensor available in the market. However, the required range linearity and accuracy can limit the selection. Okay. In the final selection of a sensor, other factors may have to be taken into consideration, such as remote indication, error correction, calibration, vibration, sensitivity, size, response time, longevity, maintenance requirement, and the critical one is the cost actually. Okay. The choice of sensor device in instrument should not be degraded from the cost standpoint. So, however, cost play a very vital criteria when you're choosing the sensor. However, you cannot jeopardize and you cannot eliminate. For example, the sensitivity, the longevity of the sensor. Apa ni semata-mata untuk mengejar ataupun untuk mendapatkan sensor yang lebih murah. Okay, due to the cost. Okay. So you must not jeopardize other criteria in the selection of sensor because you want to get a sensor with a cheap cost. Okay, there is not the is not apa it cannot be jeopardized. Okay, process control because process control is only as good as the monitoring element itself. Okay, range and accuracy. Okay, table A in the next slide will give the temperature range and accuracy of the temperature sensor. The accuracy shown are with the minimal calibration or error correction. Okay, the range in some cases can be extended with the use of new materials. Table B will give you summary of temperature sensor characteristic. So the table A that I mentioned previously, the table A show you the temperature range and accuracy of the temperature sensor depending on the type. Okay, you can see here there are a lot of temperature sensor such as expansion, pressure spring, resistance, thermistor, thermocouple, and also a semiconductor IC. You can see also the temperature range and also their accuracy. Okay, compare between each type of sensor in this table. Okay, whereas table B show you the summary of the sensor characteristic itself. You can see the advantage and disadvantage of each sensor so that you can make a comparison which sensor you want to choose for certain type of application. Okay, when you have once you have already choose your sensor, you must conduct an installation. So in terms of installation, care must be taken in locating the sensing portion of the temperature sensor. It should be fully encompassed by the medium whose temperature is being measured and not in the contact with the wall of the container. So the sensor must be in contact with the medium that you want to measure, not on the wall of the container that contain the medium. Okay, the sensor should be screened from reflected heat and radiant heat if necessary. Okay, the sensor should also be placed downstream from the fluid being mixed to ensure that temperature has stabilized, but as close as possible to the point of mixing to give a fast as possible temperature measurement for good control. Okay, and we must also allow thermal time constant in the sensor is necessary for a quick response. Okay, compensation and calibration may be necessary when using pressure spring device with long tube. Okay, especially when accurate reading are required. Okay, pressure. Okay, when we are talking about type of sensor, you will encounter the relationship between type of sensor and also pressure. Okay, pressure is the force exerted by gas and liquid due to their weight, such as pressure at the atmosphere on the surface of the earth, and the pressure containerized liquid exerted on the bottom and wall of a container. Okay, the pressure unit are measure of the force acting over a specified area. Okay, it is common expressed in pound per square inch, sometimes pound per square foot in English unit, or a Pascal in metric unit. Pressure, so how you calculate pressure? Pressure is a force divided by the area. Okay. Okay. So this example, this shows table show you the specific weight and specific gravity of some common material, together with an example how to calculate a pressure for a materials. Okay. Okay. When you are talking about pressure, there's a lot of pressure that you need to know. It's not limited to one pressure only. There is static pressure, dynamic pressure, and also impact pressure. They appear. Okay, we are working in process instrumentation plant. Okay, static pressure is the pressure of a fluid or gases that are stationary or not in a motion. Okay, point here is the considered as a static pressure, although the fluid above it is in flowing. So kat sini at the junction here is known as static pressure. Although the fluid is flowing, however, at this section is known as static pressure. Dynamic pressure is the pressure exerted by a liquid or gas when it impacts on the surface or an object due to its motion or flow. Okay, in figure above, the dynamic pressure is B minus A. Okay, you see here B minus A, and then we will get the dynamic pressure. Whereas the impact pressure, or known as total pressure, is the sum of the static and dynamic pressure on the surface of a object. Okay, point B in figure depict the impact pressure. Okay, so you can see here this is B, this is impact pressure. So the impact pressure is the sum of the static pressure added with the dynamic pressure. So it is known as impact pressure or total pressure. Okay. Manometer are a good example of pressure measuring. So when talking about pressure, one of the type of device that can be used to measure pressure is manometer. Manometer is a good example of pressure measuring instrument, though they are not as common as they used to be because of the development of new, smaller, more rugged, and easier to use pressure sensor. So nowadays, manometer has not already has no longer gain gain traction to be used in process instrumentation to measure the pressure, because we have already been replaced with more sophisticated pressure measurement device. Okay, U-tube manometer consists of U-shaped glass tube partially filled with a liquid. Okay, when there are equal pressure on both sides of the liquid, okay, the liquid level will correspond to the 0 point on the scale as shown in figure A. Okay, the scale is graduated in pressure unit. Okay, when a pressure is applied in one side of the tube, okay, that is higher than the other side, okay, as shown in figure B, the liquid rise higher in the lower pressure side, so that the difference in the height of the two columns of the liquid compensate for the difference in pressure, as shown in the equation below. Okay, the pressure difference is given by pressure R, okay, minus pressure L equal to the specific weight of the liquid in manometer multiplied by the difference in the height of the liquid in the column itself. Okay. So this slide show you the example of how to calculate uh, how to calculate the pressure in a manometer. Okay, together with a solution. So to give a better understanding how the principle of manometer working condition. Okay. Okay, so there are a lot of there are other type of manometer. Instead of U type, there are also type inclined tube manometer. It's being exhibit in the diagram A, whereas there are well type manometer, in which is represented in the figure B. So you can there instead of using U manometer, you sometimes can also sometimes encounter inclined tube manometer and also well type manometer. Diaphragm and capsule and below. Okay, gauge are major group of pressure sensor that measure pressure with respect to atmospheric pressure. So instead of using manometer, sometimes you can also use gauge to use to measure ataupun to calculate, okay, atau to sense pressure. Okay, gauge sensor are usually device that change their shape when pressure is applied. So the gauge sensor is different from manometer. Okay, so it's actually the gauge itself will change shape because of the pressure applied to it. Okay, this device of the also gauge sensor, it also can include diaphragm, capsule, or below. So this example of gauge sensor device. Okay, which is A here represent diaphragm, B here represent capsule type of gauge sensor, and below figure C here present below type of gauge sensor. Okay. For a diaphragm consists of thin layer of film of a material supported on a rigid frame as shown in figure A in the previous slide. Okay. Pressure can be applied on one side of the film for gauge sensing, or pressure can be applied to both sides of the film for a differential or absolute pressure sensing. Okay. A wide range of material can be used for the sensing film, from rubber to plastic to for low pressure device, silicon for medium pressure, or stainless steel for high pressure. So the wide range of material can be used as the sensing film. So the variety range depending on the type of pressure, whether it's low pressure, high pressure, or medium pressure. Okay. When pressure is applied to the diagram, okay, the film distorted or becomes slightly spherical. Okay, this movement can be sent using a strain gauge, piezoelectric, or change in the capacitance technique. Okay, or which is type of auto technique included magnetic and carbon pi device. Okay, the deformation in the above sensing device use transducer to give electrical signal. Okay, of all these devices, the micro machine silicon diaphragm is the most common used industrial pressure sensor for the generation of electrical signal. Okay, so here figure here show the cross section of various type of micro miniature silicon pressure sensor die. Okay, whereas the figure B here show a package micro miniature gauge sensor. Okay. For pressure sensor type capsule, is actually is a two diaphragm joined back to back as shown in the figure B. Okay, pressure can be applied to the space between the diaphragm. Okay, the space between them to forcing them to apart to measure the gauge pressure. Okay, the expansion of the diaphragm can be mechanically coupled to an indicating device. Okay, the deflection in the capsule depend on its diameter, material thickness, and elasticity. Okay, material used are phosphor, bronze, stainless steel, and also iron nickel alloy. Okay, the pressure range of major instrument using this material is up to 50 psi or 350 kilopascal. Okay, capsule can be joined together to increase sensitivity and mechanical movement. So the capsule type of pressure sensor can be joined together to increase their sensitivity. Okay. Another type of pressure sensor is a below. Is below. Okay, below are similar to capsule, except that the diaphragm, instead of being joined directly together, they are separated by a corrugated tube or tube with convolution, as shown in figure C. So the diaphragm here is being separated by the corrugated tube. Okay, when pressure is applied to the below, is elongated by stretching. Okay, the convolution and not the end of the diaphragm. Okay. The material used for the below type of pressure sensor are similar to those used for the capsule, giving a pressure range from the below of up to 100, 800 psi or 5 megapascal. Okay, below device can be used for absolute and differential pressure measurement. Okay, Then another type of pressure sensor which is known as Bourdon tube. Okay, okay. Bourdon tube are hollow, cross-sectional beryllium copper or steel tube shape in a three quarter circle as shown in the figure A here. So the figure here here you show the Bourdon tube which consists of a hollow cross-sectional beryllium copper or steel tube shaped into a three-quarter circle. Okay. They may be rectangular or oval in cross-section, but the operational principle is that the outer edge of the cross-section has a larger surface than the inner portion. Okay. When pressure is applied, the outer range has a proportional larger total surface area applied because it larger surface area and the diameter of the circle increase. Okay. The wall of the tube are between 0.01 to 0.05 in thickness. Okay. The tube are anchored at one end so that when pressure is applied to the tube, it tries to strengthen and doing so, the free and at the end of the tube move. Okay, this movement can be mechanically coupled to a pointer. Okay, which then calibrate, which indicate pressure as a line of sight indicator, or it can be coupled to a potentiometer to give a resistance value proportional to the pressure of the for the electrical signal. Okay. So figure B here show you how the movement of the Bourbon tube when pressure is applied to it. Okay. Okay. The Bourbon tubes date from the 1840s. Okay, meaning that the Bourbon is being developed long time ago. Okay. It is reliable, it is inexpensive, and one of the most common general purpose pressure gauge. Okay. Bourbon tube can withstand overload up to 30 to 40% of their maximum rate load without damage, but if overload may require calibration. So when it's overload, it need to be recalibrated. It's not them being damaged. It can also can again be used. However, it need to be calibrated first. Okay. The tube can also be shaped into helical or spiral shape to increase their range. The Bourbon tube is normally used for measuring positive gauge pressure, but can also be used to measure negative gauge pressure. Okay. So if the pressure on the Bourbon tube is lower, then the diameter of the tube also reduces. Okay. This movement can be coupled to a pointer to make a vacuum gauge. Okay. So the Bourbon tube can have a pressure range up to 1000 psi or 7700 megapascal. Okay. So this example to the Bourbon tube type pressure gauge for negative and positive pressure. Okay, for negative pressure is being represented by figure A. To measure positive pressure is being represented by figure B. So this is how the Bourbon tube type pressure look based on their based on type of pressure that they want to measure, whether it's positive, negative, or positive. Okay, so for today, this is the end for this part of presented lecture. Okay, so we end our lecture in slide number 59. So for the next part of my lecture, I will start with slide number 60. Okay, so I hope you can go through the video and you can go through also the slide which I already share with you. If you have any difficulty in understanding, you can contact me. I hope you are doing okay, and also I hope you are staying safe at home. Please go through the notes and then have a strong will so that and also you must know that all the difficulties will eventually end. Hopefully we pray for this COVID-19 pandemic will end, and so we can conclude our we can again have a lecture, have a physical lecture like those day. Okay, inshallah. So have a nice day, stay safe and stay home. Assalamualaikum dan salam sejahtera. Many thanks.